Okay, 1636 says, write the following, or the formula for the conjugate acid of each of the following. So, F minus, the conjugate acid of whatever chemical is the chemical with an extra proton, right? So, the conjugate acid would then be FH, all right? B, N2H4, N2H4, the conjugate acid would have to have another H. Now, it's an H plus, right? So this is going to be N2H5, but we're going to get the plus sign. Here we didn't get a plus sign because we had a minus sign, and that plus sign combined together to make it a neutral compound. C is C5H5N. C5H5N. The conjugate acid then, C5H5NH with a plus sign, okay? Now we could have written that with the hydrogen here, C5 or C5H6 and with a plus sign, but that H there identifies that it's acidic. That proton is acidic when it comes on and off. Okay, what else do we got? We're on A, B, C, D, O2, 2 minus. O2, 2 minus. Is that right? Yep. So that's going to be O2H with a 1 minus charge, right? Or HO2. I wrote it that way because we're used to seeing H2O, but it could be O2H minus like that. That's the conjugate acid for it. Alright, so we're on 1636E. HCrO4 minus, and the conjugate acid would be H2CrO4. Alright. 1638. Identify the conjugate acid base pairs in the following reactions. HNO3 is the acid. NO3 minus is missing a proton, so that's the conjugate base. Right? N2H4 has fewer protons, so that's the base. N2H4. It is one more proton is N2H5 with a plus charge. That's the conjugate acid. So there's the pair there. Ammonia is the conjugate base of the ammonium ion, which is the conjugate acid of ammonia, right? N2H5 and N2H4, that pair we just identified in part A. Part C, we have H2PO4, that's the phosphate ion with 2 protons. And then we have HPO4 2 minus. So H2PO4 minus went to HPO4 2 minus. This has one more proton than that, so this is the pair. This is the conjugate acid, and that's the conjugate base. The other one is the carbonate ion and the bicarbonate ion. The bicarbonate ion, HCO3 minus, has the proton. The carbonate ion doesn't. So there's the pair. The HCO3 minus, the bicarbonate ion, is the conjugate acid of the carbonate ion. And the carbonate ion is the conjugate base of carbonic acid. All right, HiO3 goes to IO3 minus. HiO3 is the conjugate acid. HC2O4 minus goes to H2C2O4 minus. H2C2O4 minus. Sorry, no minus there, just H2C2O4. HC2O4 minus. This is the conjugate acid. That's the conjugate base. All right, that's that pair. Oops, that was 1638. 1638, 1640. Choose the stronger acid. All right. So, HBr and HCl. What makes the stronger acid? The stronger acid is the one that can release the proton easier. All right. So, if we were to draw something like this, get an idea of what it looks like. Here's the bromide ion, or the bromine atom. And it's not really an ion yet. Until it falls into solution, it becomes ionized, right? And here's the hydrogen atom. All right, so these are This is molecular hydrogen bromide, right? When it's placed into the water, then the hydrogen is going to leave. When it leaves, the bromine has to now take and that extra electron, and so it's going to, size is going to grow a little bit, right? And it's going to become a negative charge. And the H plus is going to leave, and it's going to be slightly, or much smaller. It's going to not have an electron on it now, right? So the bromide ion is going to take an extra electron. The chloride ion would do the same thing. If we were to draw HCl up here, chloride ion is smaller. How do we know the chloride ion is smaller? Because it's higher on the periodic table, fewer electrons. Chloride atom and ion are smaller than the bromide atom and ion respectively. Chloride ion is larger, takes on that extra electron. And who can hold on to that extra electron better? Well, the bromide ion can hold on better because, why can it hold on better? Because there's more protons and an extra electron, once you have, like bromide has how many kids? It has 35 electrons, 35 kids. The 36th is not nearly as much as going from 17 to 18, right? So because 1/17 is a higher number than 1/35th, then bromine can maintain that negative charge better. And the ability to maintain that negative charge is also related to the ability to release that proton. So that means hydrogen bromide is going to be a stronger acid. Water and HF. This is the next comparison. Choose the stronger acid, H2O or HF. Water, we don't really think of it as an acid, right? But HF can bind pretty tightly to its protons, so you might think for a second that HF is not as a strong acid as water, but oxygen, hydrogen, there's, let's look at the periodic table, make sure we're looking at this right. Yeah. So, HF is definitely going to be a stronger acid. I mean, water is barely an acid, right? I mean, it can act acidic to a degree, but not to any significant degree. So hydrogen fluoride is a weak acid, and it's going to be stronger. Okay. The last pair is what? H2S or HBr? Well, that one's easy because we know that one is a strong acid and one's a weak acid. H2S is not a strong acid. The 6 strong acids, HBr, HCl, HI, H2SO4, HNO3, sulfuric acid, nitric acid, hydrobromic, hydrochloric, hydroiodic, HClO4 perchloric acid, and chlorous acid in this book as well. All right, 1642. 1642. Choose the stronger acid and give your reason. HOCl and HOCl2. HO2Cl and HClO2. So we have this compound here where there's one oxygen. Now both of these are oxyacids. That's important to recognize because what governs oxyacids is a little bit different than what governs binary acids in terms of strength. Okay? The oxyacids are governed by how, again, it's all about how easily that proton can come off because that's what determines the strength of an acid, how easily it gives up a proton in aqueous solution. And if this proton is going to come off here, then this oxygen is going to need to take a negative charge and form OCl with the minus sign there, right? If this occurs, that negative charge has the ability to kind of be distributed between this oxygen and that chlorine. Now the oxygen is the electron hog, but the chlorine will take some electron density. On the other hand, if this compound, ClO with a negative charge, ClO2 with a negative charge, is going to be formed when this proton is left, right? That electron density has the ability to be sucked across to this other oxygen. So we have an increased ability to stabilize that negative charge, and that's an increased likelihood or ability to remove that proton. So this will be our stronger acid. In oxyacids, the one with more oxygens will stabilize that negative charge better and becomes the stronger acid. All right, that was 1642, but that was only A. We got to do part B as well. 1642B, H2SeO4 and H2SeO3. H2SeO4 was first. So we have 4 oxygens and 2 hydrogens. We could draw these to find out, but I'll bet that those are double bonds like that. So H2SeO4, there we are. And we want to compare that to H2SeO3. SeO, not H2, just HSeO3, right? Oh, it is H2. Okay, kind of like the sulfate and the sulfite, right? Selenate and selenite ions. So, which one is going to be able to release a proton easier? Well, once this releases a proton, then once this one releases this proton, then that negative charge can be stabilized in different spots. We have other resonance structures which we can draw, where we can have the negative charge come over here or over here. So this one is going to be the stronger acid. It's going to release that proton easier than this one, so this one is the stronger acid. Choose between the stronger acid HClO3 and HiO3. This is 1644. 1644 HClO3, HiO3, ClO, and IOO. All right, so now we have the same number of oxygens on these 2 oxyacids, but now which one is going to be able to stabilize the electrons better? Now it has to do with electronegativity. Which one of these ions here can pull the electron density away from the new proton or the new negative charge that's going to form, right? So chlorine is more electronegative. So this, now before, the iodine had in binary acids, so don't get confused with binary acids. In binary acids, when the proton leaves, the proton has to be absorbed by the iodine, and the iodine has more electrons and more protons to kind of allow that one electron to get lost in. But in this scenario here, what we're describing it as, the more electronegative one has the ability to stabilize the negative charge that's going to form. So if we form that negative charge here, and we form this negative charge here, which one of these is going to be more stable? Well, they have the same number of oxygens for this negative charge to kind of run to stabilize itself. But chlorine also wants a little bit of electron density. Iodine does too, but not as much as chlorine, because chlorine is more electronegative. All right, 1644B. HiO2 or HClO3. 1644 HiO2 or HClO3. Well, HClO3, HiO2, was that it? Whoops. Okay. Is that what they're asking? HClO3, HiO2 and HClO3, yeah. So in this case, we can either choose and this one has to be the stronger acid, right? It has more oxygens and it has the more electronegative center. So in both for both reasons, we could identify that this one is the stronger acid. All right, then we have the last one, 644C, H2SeO3, HBrO4. H2SeO3 H2SeO3. What's the other one? HBrO4. Oops, HBrO4. So here we have more electrons, more oxygens, here we have fewer oxygens, so we would vote for the bromine there for that reason. We also know that bromine, well, we can look, how does the electronegativity of selenium compare with bromine? Bromine is further to the right, so it would be more electronegative. So for both reasons, this one would be the stronger acid there. 1646. The ion chromium hexahydrate is weakly acidic. All right, so chromium has a way to form an ion in which we have six water molecules coordinated to it. And this whole thing has a +3 charge. And that chemical is weakly acidic, they say. If it's weakly acidic, that means you put it into water and a little bit of a proton comes off, right? That's what weakly acidic refers to. So, write an equation showing the behavior as a Bronsted-Lowry acid in water. So if it's weakly acidic, then there's another water molecule nearby. It is going to somehow make protons, right? Well, or the hydronium ion. One of these hydrogens has to leave. And water here, we'll draw it out, with its lone pairs is going to attack one of these protons. And the result, after it's attacked it, right, we're going to get that proton coming up here, and this species is going to have a positive charge, and this species is going to be left with an additional negative charge, which when combined with the +3 will make a +2. All right, so 1646. Yep. Oh. In terms of writing the compound, CrH2o, now we have, instead of 6, we have 5, and then we have the OH, and then the net charge on it. Okay? All right. 1648. Use the Lewis symbol to diagram the reaction between NH2 and minus a proton to form ammonia. Okay, we want to identify what happens when we have NH2 with a minus charge. So 1, 2, 3, 4, 5, 6, 7, 8. That's what that looks like. Plus an H plus ion, and the product is going to be NH3, right? So what's occurring here is these free electrons are coming and grabbing that proton. And the result is this compound here. Alright, so that is our Lewis dot structures, and we're showing how the reaction occurs. Oh, when you have ions, they're supposed to be in parentheses like that. Negative charge. 1650, beryllium chloride exists as a solid polymer. Kind of a weird chemical. Alright? BeCl2, beryllium dichloride. Composed of a long chain of beryllium and chlorine. The formula for the chain can be represented as BeCl2 with an N, meaning N is how many repeats there are in this long unit. That's what you normally do when you characterize or name polymers. Use Lewis structure to show how the reaction BeCl2 goes to BeCl2N. So, if I have show how the reaction is a Lewis acid-base reaction. So if we have BeCl2, so we can draw this, and it is going to interact with another, BeCl2. So the chemical reaction that they write is BeCl2 N values, and the result is going to be BeCl2, and we're going to get N of them forming some chain, right? This is, so they have N. So if we just choose 2 to start with, then how are these going to come together? Well, they showed us the structure there. So what it looks like happens is that this beryllium here, now beryllium has, what does the Lewis structure of this thing actually look like? Let's just draw that. Beryllium brings, is that 3 electrons? 2 electrons. Beryllium brings 2 electrons. Chlorine brings 7. So you have 14, 15, 16 electrons all together. And so this is what the Lewis dot structure of beryllium chloride looks like. And it looks like that beryllium, because this chlorine has to connect to this next beryllium here, right? Because the product, as shown in the book, beryllium, chloride, chloride, beryllium, right there, right? And then it continues. Okay, so it looks like that these electrons here, now in this model product, they only have 2 electrons on the two lone pairs. So it looks like these electrons here are going to attack that there and form a bond between there. These electrons are also going to attack there. Right? So if I had a third beryllium chloride in here, if the N value that I wanted to choose was 3, these electrons would be attacking that beryllium there. Alright, so that looks like how the polymerization of beryllium chloride is. Okay, now they didn't draw it like this, they drew it like this, which is a little more confusing, but same thing. Alright, 1652, the Lewis structure to diagram the reaction of carbon dioxide with water. Alright, 1652, the Lewis structure to diagram the reaction between carbon dioxide, carbon dioxide and water to form carbonic acid. Or use the Lewis structure. Identify the Lewis acid and the Lewis base in this reaction. So here's carbon dioxide. Now we need to use the Lewis structure. Oops. Right? And it's interacting with water. And the product is H2CO3. All right, H2CO3. Yeah. Okay. So, what's occurring here? It looks like the water here is somehow getting connected to that carbon. Well, the electrons have to be the one that do the attacking because they're the ones that are going to move. So it looks like the electrons from this oxygen attack that carbon. And it also looks like one of these protons leaves because as soon as this gets attached, it ends up with just an OH, right? Not an extra OH, an extra H. So it looks like also we have one of these sets of electrons grabbing on to that proton. All right, so it looks like there's two steps. Identify the Lewis acid and the Lewis base in the reaction. Well, the Lewis acid is the one that accepts the share in the electron pair. So who is accepting a share in an electron pair? Now, I don't know if this is a concerted reaction, which means that this happens at the same time, or if it's a stepwise reaction, where one happens first and then the other happens. If it's a concerted reaction, there would be an argument that this is the Lewis acid and this is the Lewis acid. But for all intents and purposes, this is the step that's probably the most important one that's going to happen first. This proton eventually gets there, but it could be coming from somewhere else as well. It could be getting it from a different water, and this proton could be going to a different water molecule. So this is the one that they're going to use to identify whether it's a Lewis acid or Lewis base. Who's accepting the share in the electron pair? Carbon dioxide is accepting that share, so carbon dioxide would be the Lewis acid. All right, so let's see, make sure that we're not missing anything special about that one. 1652. Oh, the other thing that they showed was that after this gets a proton, then these electrons have to come up here because oxygen won't be able to have 3 bonds to it like that. So, all right, good. 1654. Use Lewis structures to show how the following reaction can be viewed as a displacement of one Lewis base by another. The chemical reaction is NH2 minus plus water. Might as well draw these Lewis structures. We're forming ammonia. And hydroxide ion. And we want to use Lewis structures to show how the following reaction can be viewed as a displacement of one Lewis base by another Lewis base from a Lewis acid. Identify the two bases and the Lewis acid. Displacement of one Lewis base from another Lewis base. Well, what's going on here? It looks like this thing is going to take a proton from here, correct? So these electrons here take that there. And when that occurs, these electrons go back onto the oxygen and form an OH minus. So this has 3 lone pairs of electrons on it. And so if you're thinking about it that way, then this is the Lewis base, because this is the water is accepting a share in electron pair. It's the Lewis acid. But they said, what did they say? Identify Lewis structure to show how the following reaction can be viewed as the displacement of one Lewis base by another Lewis base from a Lewis acid. This, what is that? Is the displacement of one Lewis base by another Lewis base. So we have one Lewis base here being taking a proton here. Ammonia here is a Lewis base, And if this chemical reaction is going to go backwards, then okay, I guess what it's saying is that after this chemical reaction happens, the Lewis base is here and we form a Lewis base. So, and then it says identify the two Lewis bases. This is a Lewis base, but then this is also a Lewis base. Okay. Oh wait, did I say that right? Let's see. In this chemical reaction here, this is now the Lewis acid because it's accepting a shared electron pair. This is the Lewis base. This is the Lewis acid in this chemical reaction. NH3 and water in that chemical reaction, this is our Lewis base, right? We have NH and protons, then we have water, and this forms NH4 plus and OH minus. This there, this is the Lewis base. This is accepting a share. So I'm not exactly sure what they're trying to say by show that following reaction can be viewed as the displacement of one Lewis base by another Lewis base from a Lewis acid. I don't know what they're saying there.